problem 5.36. It asks us to find the magnetic field at some point offset from the center of a square loop with current I. For this, I am going to start with this formula, this term right here. This is the magnitude of the magnetic field produced by a segment of wire at a position, a distance r from the center of that segment of wire. Now, because we are dealing with a square of side w, that is 4 segments of wire, each of length w. So I've put the w in right here. And so that is what I'm going to start at. Now, having, say, 2 of these segments of wire that are opposite each other on the square, when they're both going to create a magnetic field. Now, I can, through manipulating the direction the current travels, I can say that in the z direction, that is the direction normal to the square, they both will create magnetic field in the same direction. I'm going to go ahead and say it's directed upward. However, in a direction along the plane of the square, they will both create magnetic fields in opposite directions. And because of the symmetry of the problem, they will, by necessity, be equal. So I have this magnitude of magnetic field. I want to find its z component. Now, its z component is not as simple as it's not as simple as when we did something like this for electric field, because the magnetic field does not go in the direction of electric field. However, it goes perpendicular to the direction of electric field, which means that we can still use the trick that the z component is proportional to the magnetic field, is proportional to the perpendicular distance, which in this case is half the size of the square, and inversely proportional to how far away. This is basically the sine or cosine of theta, depending on which theta you select. So combine that, so put that into here, and you would get Bz is equal to mu sub naught I w squared over 8 pi r cubed. Put in the 2 to 4 to make 8. R and r squared becomes r cubed, and w squared. We can also use the Pythagorean theorem to say that r is the distance from the center point of our wire to the point of interest. So it goes 1/2 of w, or 1/2 the length of the square, to get towards the center, and then it's offset by a distance z. So Pythagorean theorem, r is equal to the square root of w over 2 squared plus z squared. Put this in, and we get the formula, and multiply by 4 because there are 4 sides, and we get the z component of the magnetic field at a position offset from the center of the square, given by this formula right here. So this is the total magnetic field at that position. Now the other part of the question says, verify that it reduces to the field of a dipole with the appropriate dipole moment. Well, when z is much bigger than w. Well, when z is much bigger than w, to first order, we can just eliminate this term right here, the w over 2, because z is much, much bigger than that. And now I'll admit, when I first did this, I went in assuming that I would still have to keep the first order term. Actually, we don't, not for this. It works just with this lowest order term. So eliminating, and actually you can see that's what I did right here. I pulled it out. But this basically goes to 1 as long as w is much smaller than z. So b is approximately mu sub naught I w squared over 2 pi z cubed. Now, I am going to use the formula 5.89 for the magnetic field produced by a dipole. Magnetic field produced by a dipole, mu sub naught over 4 pi times 1 over r cubed. And this is a neat little trick. I recommend you keep that in mind. M is the dipole moment vector. R is in our case z. but so r hat points in the z hat direction. Now, for us, because we are looking solely at a point on the z-axis, and which is on the direction normal to the square, our dipole moment direction is the same as the r direction, which means m dot r hat is the magnitude of m, and the magnitude of m times r hat is just the m vector. So this reduces to 3m vector minus m vector, or 2m vector. Now, keep in mind this is only true because we are parallel to r hat, because m is parallel to r hat. It would also be true if m is anti-parallel to r hat, but any other direction it would not work. So this just reduces to 2m. Now, the dipole moment for a current carrying loop, as long as that loop is flat, which our loop thankfully is equal to the current times the area of the loop. And since we're dealing with a square, the area of the loop is w squared. So replace this all with 2w squared, and we get mu sub naught, or 2iw squared. We get mu sub naught times iw squared to give our numerator. We get the 2 from this term to turn that into 2 pi, and r is z, so r cubed becomes z cubed.